Hello, I am Hasan Murat Sümer and this is my project presentation for the Magnetic Resonance Imaging course. My project title is MATLAB Simulation of FIESTA Pulse Sequence, and in the simulation I have tried to cover as many concepts as possible I have learned throughout the course, and some of the concepts I've covered are selective excitation and refocusing, relaxation, rotation matrices, steady-state free precession imaging, inversion recovery techniques, signal acquisition and image reconstruction. So first of all, let me show you the phantom which I have used for my project. There is an open source numerical MRI simulation package called MRI Lab, which can be acquired from SourceForge. This simulation package comes with various phantoms, including a high resolution brain phantom which I have used. Other than this phantom, I did not use any MATLAB code or MATLAB data from an external source. So this phantom is a structure which includes multiple 3D matrices which represent the brain. Its size is 180 pixels in X direction, 216 pixels in Y direction, and 108 pixels in Z directions. Dimensional resolution is 1 mm. It consists of white matter, gray matter, and fluid tissues, and the values of relative spin densities to water, T1, T2 and T2 star of these three tissues are also included in the structure. So 180 pixels in Z directions correspond to 180 slices. To show you what the slices look like, I will display the slices at Z equals 45, Z equals 91 and Z equals 135 locations. So the purpose of the simulation is to scan and reconstruct the slice at Z equals 91 plane. Also note that these images here are colored according to the spin densities of the tissues. So the brightest parts are the fluids, second brightest parts are the gray matter, and the darkest parts are the white matter. So what is FIESTA? FIESTA is an acronym for Fast Imaging Employing Steady-State Acquisition. It is the trade name of General Electric for Balanced Steady-State Free Precession Imaging Sequence, or Balanced SSFP in short. Siemens calls theirs TrueFISP, so FIESTA and TrueFISP are basically the same thing. They are a category under gradient echo sequences. Here you see a typical FIESTA sequence. There are two critical properties to notice here. First, the RF pulse changes sign in every repetition of the sequence, so we have alternating RF pulses. Second, the total area under each gradient is zero, so by the time the next RF pulse is applied, the gradient effects will cancel out. A common practice is to apply alpha over 2 flip angle RF pulse before starting the first sequence. For example, if the flip angle of our RF pulse is plus minus 60 degrees, first we apply a 30-degree pulse in X direction, so the initial magnetization is tilted 30 degrees to the Y-axis. With this case, when we apply minus 60-degree pulse, the magnetization will be tilted 30 degrees in minus Y-axis. So in two states, despite having opposite faces, the magnitudes of transverse and longitudinal magnetizations will be the same. In reality, however, in the time between two RF pulses, the relaxation effects will tilt the magnetization towards Z-axis. This is where the term steady state comes into play. If the sequence repetition time is short enough, a steady state for the magnetization will exist, and with each application of alternating RF pulses, the same value for the magnitudes of transverse components will be achieved in the steady state. A common practice to put magnetizations in steady state is to apply a series of alternating pulses before beginning signal acquisition. With enough number of pulses, the steady state will be reached. Another method to achieve steady state is to use inversion recovery methods. Applying an inverting pulse and waiting for inversion time Ti before applying the alpha over 2 pulse may help achieving steady state quickly. But for three different tissues, a single inversion pulse will not be enough. Also, if a single inversion pulse is applied, the reconstructed image's contrast will be affected by the value of Ti. If we desire to achieve steady states quickly for gray matter and white matter, we can use double inversion recovery. We apply an inverting pulse, we wait for time ti1, then we apply another inverting pulse and wait for time ti2 before applying alpha over 2 pulse. By carefully selecting ti1 and ti2, we can achieve this steady state very early in the experiment. I will demonstrate results for both single and double inversion recovery methods. What you see here is the exact sequence I have simulated. The period of the sequence is 6 milliseconds, so is the sequence repetition time. You can see that gradients gx and gy are never applied in existence of gz. I prefer this way because the methods I use to compute magnetizations is different. During excitation and refocusing, I create and use rotation matrices for an axis which represents the effective B field in the xz plane. During phase encoding and signal acquisition, I use the fact that the derivative of the phase is proportional to the B field in z direction. This huge value of 50 Tesla over meter for GZ gradient you see is a result of a design error which I made very early in the project. It is the value required to excite a volume of 7 mm thickness or 7 planes, which has the z equals 91 plane in the middle. Other than being unrealistic, it doesn't cause any problems though. The duration of the RF pulse is 1 millisecond. The envelope is a sinc function with 3 side lobes and it's windowed with a Hamming window to reduce Gibbs effect. The amplitude can be adjusted to have any desired flip angle. I will also demonstrate results for RF pulses for different flip angles. Note that the pulses are always applied in x direction. After the RF pulse is turned off, GZ remains on for another half a millisecond for refocusing. When GZ is turned off, GX and GY are turned on. GX is negative for half a millisecond and GY is on only when GX is negative. The signal acquisition is performed when GX turns positive for a duration of 2 milliseconds. In the middle of this period, the echo is formed. The time step size of this simulation is 10 microseconds. So in one phase encoding experiment, 200 samples are collected in readout direction. 432 phase encoding experiments are performed in total in the simulation. So we have 432 samples in the phase encoding direction. During signal acquisition, I have used the magnetic oscillator model provided in the textbook under the title Alternate Derivation Signal Equation. In this model, the signal is given by this formula which we integrate the transverse magnetizations in a plane, keeping their phases in mind. Derivative of the phase is given by frequency, and frequency is proportional to the B field by Larmor relation. So as the gradients Gx and Gy affect the B field, the resulting phases can be computed by using numerical methods. By preference, the signal can be collected by only considering the contribution of z equals 91 plane. If this is the choice, the runtime of simulation is about 8 minutes. Or we can include the contribution of all 7 excited planes to the signal. In this case, the formula of the signal is given by a triple integral. However, if this is the choice, the simulation runs for half an hour. Because of this issue, I will not run the simulation here. Instead, I have recorded the workspace for 7 proper simulations into the path folder, and I will demonstrate the results of these 7 simulations by loading them into the MATLAB. Before going into results, I will reference this article here to show what we must expect from FIESTA sequence. Our true FISP images T2 over T1 weighted. If I summarize, the article states that the image contrast for FIESTA true FISP sequences depends on the combination of proton density and T2 over T1 ratio. For larger flip angles, T2 over T1 ratio is more effective, and for smaller flip angles, the proton density dominates and the contrast between the gray matter and the white matter significantly decreases. It also states that how quickly the steady state is achieved affects the image. To give an idea, this is an image colored by the T2 over T1 ratios of tissues. We see that white matter is the brightest tissue, the fluid is also very bright, and the gray matter is the darkest. But because the fluid has the highest spin density, it will appear as the brightest tissue in double inversion recovery images. Keep in mind that these T1 and T2 values come from the data of Brain Phantom and do not necessarily reflect the exact reality. So for the first 6 simulation results I will display are results for when only the contribution of z equals 91 plane to the signal is considered and other planes are ignored. First, I will show a simulation which plus minus 60-degree pulses are used and the magnetizations are prepared with double inversion recovery, where Ti1 is set to 0.8 seconds and Ti2 is set to 0.44 seconds. So if we look at the progression of transverse magnetization of tissues, we see that gray matter and white matter reached steady state very quickly. Gray matter transverse magnetization has value of 0.11 and white matter transverse magnetization has value of 0.13, so the white matter will appear brighter than the gray matter. We see that fluid transverse magnetization did not reach steady state at all, but its decay is very slow because of its very high relaxation time constants, so it is somewhat steady, and it decays from 0.2 to 0.17, which is significantly higher than both gray and white matters, so it will be significantly brighter in the image. I will display the reconstructed images for different simulations with the same color map in order to compare the signal intensity. If we look at the resulting image of this simulation, we see that the reconstructed image has the contrast we have expected. The fluids are very bright and gray matter is darker than the white matter, and the contrast between them is good enough to differentiate them visually. The Gibbs ringing artifact due to truncations is visible in the image. There is another artifact in this image which I believe not apparent in the video recording, is a very weak blurry shift in both horizontal and vertical directions. It will be more visible in one of the next simulations, so I will talk about it later. The next demonstration is from a simulation which, again, plus minus 60-degree excitation pulses are used, but this time single inversion recovery is used and the inversion time is 1 second. We'll see that the image will be drastically affected. In this case, the fluid's longitudinal magnetization will not even recover to a positive value when the signal acquisition is started, and as a result, until 1/3 of the experiment is complete, its phase will be opposing the gray matter and white matter and will make a destructive contribution. However, white matter's and gray matter's behavior will not be much different compared to this simulation's double inversion recovery counterpart, and they will have the same contrast, but because steady state is achieved later, image quality will be a little affected, and because of fluid's different behavior, it will be nullified in the resulting image. In the resulting image, we see that fluid still appears with very little intensity and it's extremely dark, and we see that some shifting in tissues are noticeable around the origin and on the upper side of the image, but when we compare it to the result of the previous simulation, we see that the contrast between white and gray matter is the same. The next demonstration is a result of simulation which plus minus 30-degree excitation pulses are used with double inversion recovery applied. Both Ti1 and Ti2 is set to 0.95 seconds. Steady state is achieved very quickly for all three tissues this time. The transverse magnetization magnitude for white matter and gray matter are almost the same, so we will lose the contrast between them. But their magnitude is higher than previous simulations, so both will appear brighter. The fluid will still appear brighter than both gray matter and white matter, but it will be darker than as it was on 60-degree double inversion recovery simulation. As you can see, it is very difficult to visually distinguish white matter from the gray matter in the resulting image. The next demonstration is from a simulation which, again, plus minus 30-degree pulses are used, but we use single inversion recovery with Ti equals 1 second this time. The fluid shows the same behavior as the previous single inversion recovery experiment, and as a result it will be nullified again, but this time it will be much darker, but the contrast between white matter and gray matter will not change much. Let's look at the results of another simulation. So in this simulation, plus minus 120-degree excitation pulses are used and double inversion recovery is applied. Because the flip angle is too large, when the magnetization is excited, its longitudinal component will be very low, and the transverse component relaxes quickly, but because the longitudinal relaxation is slower, by the time the next pulse is applied, it will only recover a very little. So as a result, when it is excited again, its transverse component will also be low, and as a result the signal intensity will be much lower than previous simulations. But the contrast between the tissues will pretty much be the same. By the way, I want to say that I did not demodulate the received signal to acquire the baseband signal, because the magnetizations computed in the simulation are always in the rotating frame, and rotating frame's connection to lab frame is the same as the connection of baseband signal and the received signal, so demodulation is not necessary. The next results are from a simulation which plus minus 120-degree pulses are used and single inversion recovery is applied with Ti equals 1 second. The results are similar to the previous single inversion recovery experiments. Fluid will appear dark, but it will not appear as dark as previous single inversion recovery experiments. In this image, you see some blurry shifts on the upper side and lower side of the image. Also, you see some horizontal linings throughout. They were also apparent in weaker form in previous results. I believe they are results of some sort of weak ghosting caused by the weighted K-space. So, if we compare all the results, we can summarize that with steady state achieved early by using double inversion recovery, the middle flip excitation pulse sequences give us good enough contrast between gray matter and white matter to differentiate them. Low flip angle excitation pulse sequences give us very low contrast between the gray matter and white matter, and with high flip angle excitation pulses cause the signal intensity to diminish. And when the single inversion recovery is used with the same excitation pulse sequences, it causes the fluid tissue, which has very long relaxation time, to appear very dark. Finally, I will demonstrate a result from a simulation where the signal is acquired by integrating over a volume of 7 mm thickness or 7 planes equally, and the parameters from the first simulation are used. The flip angles of excitation pulse are plus minus 60 degrees, and double inversion recovery with the same time values are used. I will not display this image with the color map I used for previous results because it has much higher intensity. And in the image we see that aliasing occurred in y direction because of contribution of other planes, but their contribution are weak, so the ghosts will not ruin the image too much. And we see that the boundaries between tissues are somewhat smoothed. And here's a comparison of two simulation results with the same parameters, except for the method to collect the baseband signal. So finally, I want to say that the voice recording and the monitor recording of this video are performed separately because of technical difficulties. So if there's a issue about synchronization of voice and the video, I'm sorry for that. Thanks for listening.